Greetings. Welcome to the Dr. J Vlog series. It is Monday, March 17th, 2025. Happy St. Patrick's Day. And on Mondays, we look at mathematics and statistics. As with any field of endeavor, mathematics has many subfields. We all likely studied at least some of these when we were growing up, especially as we were going through school and taking classes in various branches of mathematics, algebra and geometry and so on. Maybe you got all the way up to calculus, maybe not. The point is that as we advanced in our schooling, we were also learning more and more advanced mathematics. And mathematics, of course, underlies all of the scientific disciplines, all of the different fields, as we try to map and model different phenomena using mathematics. In other words, we're always looking at ways to map patterns in nature. And we, as human beings, are, among other things, these indefatigable pattern seekers. We love to find patterns. Seems to be the way our brains work for a variety of evolutionarily important reasons. And patterns show up everywhere in nature. For example, the lovely ratios of vibrations in Western music have clear patterns. They do in all types of music, for that matter. But most of you are probably more commonly have been exposed to the patterns that we consider to be pleasant to our ears, reflected in Western music based on the vibrations, the different geometric ratios of the frequency of the patterns of the vibrations that we're hearing. And so most obviously, or one of the simplest examples of that, is when we are listening to pitch and we hear a particular note, and if we were to double the frequency of that note, the pitch would raise by exactly 1 octave. There's a mathematical certainty and precision to all of that. Or conversely, if we were to have the frequencies, we would drop the sound. We would drop the pitch by a full octave as well. So I'm going to do a vlog another day on vibrations and the mathematics of music and how that relates to what we're hearing and what sounds good to us, what's pleasant to our ears, and so on, and what sounds dissonant, etc. So there's actually a mathematical explanation too. There's a cultural explanation, but also a mathematical one. Okay, so again, there's this aesthetic quality then that accompanies pattern seeking in all aspects of nature and music and culture and so on. And I'll give you another very simple example, something you may have thought about or maybe have tried yourselves or considered at one point along the way. And that is how old you are relative to your children, or conversely, how old you are relative to your parents, right? We've all probably thought about that from time to time. And so when you were born, for example, just imagine that you were born on the exact same day, same birthday as your mother, all right? And she was 30 years old when she had you. So at that point, just after you were born, she's unimaginably older than you are, at least in terms of the ratio of how old she is to how old you are, okay? So let's say that, again, you were born on the same birthday as your mother, and then you survived that first day. Obviously you did, otherwise you wouldn't be here listening to this vlog. Okay, so at that point, though, as a 30-year-old, again, depending on how many leap years she'd been or when she was born relative to was she born in a leap year or not, whatever. But the point is that at that point, one day after you're born, your mother will have lived probably 10,958 days to your 1. So, of course, that's a huge ratio, 10,958 to 1. Okay, but what's cool is that every day that you live, of course, that ratio between the two of you is just going to decrease over time. And so when your mother turns 30, that same day when your mother turns 60, that same day that you turn 30, that ratio now will be 60 to 30 or 2 to 1, dramatically reduced since that first day. And if you have the good fortune that your mother lives to 90 and you've lived to 60, the ratio reduces further, now 90 to 60 or 1.5. So another example, somewhat more complicated example, would be Euler's identity. I don't expect most of you to know that. Some of you will, especially if you're a mathematics major, or maybe if you're just fascinated by mathematics at whatever level. I actually keep the Euler identity. It's the last line in my email signature, my e-signature. It's just my favorite equation. So, but the Euler's number, the Euler identity equation it's quite simple, and it's beautiful in its simplicity. So it's just the number e raised to the power of I times pi plus 1 equals 0. Okay, so there's 5 mathematical concepts there. E, it's a small e, raised to the power of I times pi plus 1 equals 0. Now that e is sometimes referred to as Euler's number. It's a mathematical constant equal to approximately 2.71828, often rounded off to 2.72, just like pi. The number pi is often rounded out off to 3.14, right? So what is e? That's actually the base number of natural logarithms. So again, 2.71828. The I that it's raised to is the imaginary unit. You may recall from mathematics that if you square a number, it has to be a positive number. So we invented imaginary numbers so that I squared is equal to -1. So that's the I that we're talking about, the imaginary unit, the square root of, obviously, of I squared, the square root of -1. And then that's multiplied by pi. Then we add 1. And if we do follow the mathematics, and then there are proofs of these things and actually really cool examples of how the equation was derived online, but all of that equals 0. Okay? And so many folks, they actually did a study, they did a survey of mathematicians, and this ranked number 1, the Euler identity, as the most beautiful equation in all of mathematics. Okay? Connecting these 5 mathematical constants into one perfect equation. So, in short, many of us, I think, appreciate not only the utility of mathematics, but the underlying beauty of mathematics and the many patterns in nature that can, of course, be described with mathematics. And indeed, there are innumerable patterns that have been and continue to be discovered. And within mathematics, that field continues to come up with new and interesting findings as well. Math is not over by any stretch of the imagination. In fact, there are many major problems that are unsolved, and some feel perhaps even unsolvable, that mathematicians are tackling. So there are frontiers in mathematics just as there are in every field of endeavor. So I want to focus in this vlog then, for the remainder of this vlog, on one very specific pattern, one of the most remarkable patterns that we see in mathematics, and how it corresponds to what we see in nature. Okay, and this is specifically the Fibonacci sequence. Okay, it's quite elegant in its simplicity. You probably know about the sequence, even if you didn't know the name. Some of you will recognize the name, and maybe you're already aware of the Fibonacci sequence. But it's basically the series of numbers where each number is the sum of the 2 preceding numbers. So let's start. You don't have to start at 0. In fact, some recommend that you don't for the Fibonacci sequence, but you can start at 0 and 1. So those 2 numbers are side by side, obviously, as whole numbers. But 0 plus 1 is equal to 1. All right? So now you've got the preceding equation. The 0 plus 1 is 1. And then you've got that is equal to 1. Now you take those 2 numbers and add them together. 1 plus 1 is equal to 2. And let me just jump forward here if I can. And then the sum of the 2 preceding numbers are 1 and 2. So 1 plus 2 is equal to 3. The sum of those 2 preceding numbers or the 2 preceding sums are 2 and 3. So 2 plus 3 equals 5, and so on. Okay? So you've got then f sub 0 is equal to 0, f sub 1 is equal to 1, and then if you're working forward in the Fibonacci sequence, it's actually given by this simple equation. So whatever your f sub n is, whichever Fibonacci number you're talking about, it's always going to be equal to f sub n minus 1 plus f sub n minus 2. So again, look at the sequence. 0 and 1 is equal to 1. That's f sub 2. What's the third number? F sub 3 in Fibonacci. 1 plus 1 is equal to 2. So hence the numbers. And then f sub 4, 1 plus 2 is equal to 3. Right? And then 2 plus 3 is equal to 5, and so on. Oops, didn't mean to do that yet. Okay? So that's how we calculate the Fibonacci sequence. I've listed there at the bottom the first 10 numbers in the Fibonacci sequence. And as I say, it's pretty straightforward. What's interesting about this now, where it absolutely was discovered originally, this remains disputed. Okay, the sequence though ended up being named after the 12th century mathematician Leonardo of Pisa, who in the 19th century was given this nickname Leonardo Fibonacci, or the son of the Fibonacci clan, simply because they were trying to avoid confusion with another famous Leonardo of Pisa. All right. So again, but whatever the ultimate origins, we know that in 1202 of the contemporary era, this Leonardo of Pisa published a mathematical text, Liber Abaci, that could be used and was used by the average person, the average tradesperson, whoever, to help with their calculations, everyday calculations, in a variety of different contexts. And in that book, he introduced what we now refer to as the Fibonacci sequence. At least he introduced it to the Western world. Okay? And in that book, he also included this cute example of rabbits. Okay? So he essentially what he does is he conducts a thought experiment. So given ideal conditions, how many pairs of rabbits could be produced from a single pair of rabbits in 1 year? And he had to standardize the thought experiment in the following way. So he said that on the one hand, imagine that every time the rabbits mated, okay, they always had a pair of rabbits, one male and one female, and that they mated every 30 days, or basically once a month. Think of it that way. Okay, so how many rabbits then would they produce under those ideal circumstances? So it turned out to be 144, which is a Fibonacci number, and it could be derived from the Fibonacci sequence. So in other words, the experiment, again, requires that the female rabbit always gives birth to 2 rabbits, a male and a female, and then you leave them, or you keep them in an enclosed area so that they're going to breed on a regular basis or on a monthly basis. So the newborn rabbits, they're also called kittens or rabbit kittens, so we don't confuse them with the kitty cats. But anyway, the 2 baby rabbits, they're left in this fenced-in area to breed. And after 1 month, okay, only the original pair are still there, because rabbits, by this thought experiment, they reproduce every month. Okay, they require 1 month to be able to reproduce. So after 2 months, what happens? The first pair gives birth, and thus you now have 2 pairs of rabbits, right? And then in month 3, the original pair of rabbits produce another pair of newborns, while their earlier offspring have grown to adulthood, right? And then they will have reproduced as well. So this leaves 3 pairs of rabbits, 2 of which will give birth to 2 or more the following month. And you see how it progresses then. Each month, and it follows the, with the mature rabbits, each reproducing appropriately and once per month. Once they're mature enough, it leads to the following sequence. And after 10 months, I don't have it here on screen, it's too many rabbits, but after 10 months, there would be, following this logic, there would be 55 pairs of rabbits. And then after 11 months, there would be 89. And then you add those 2 numbers together, 55 and 89. And after 12 months, there would be 144 pairs of rabbits. And by the way, if you just extended that logic 1 more year and kept having your rabbits reproduce in that fashion, it starts going up this, geometrically, or literally in this geometric proportion, or in the Fibonacci proportion. And after 2 years, you'd actually have 46,368 pairs of rabbits. So that's how quickly they reproduce, or at least in this thought experiment. Okay. And so in nature, then, there are many examples of Fibonacci numbers appearing in sequence in the natural world. Now, to be clear, just because a series of numbers can be applied to an object doesn't mean that there's necessarily a correlation between the math and the reality. But I tell you, it certainly feels that way in many circumstances, because for whatever reasons, Fibonacci numbers keep showing up they keep showing up time and again in nature in a variety of different contexts and naturally occurring patterns. So you can commonly spot Fibonacci numbers by studying the manner in which various plants grow, such as the branching in trees. The arrangement of leaves on a stem often follows the Fibonacci sequence. The fruitlets of a pineapple, the flowering of the artichoke, and the arrangement of a pine cone. All of these follow the Fibonacci sequence. And if you look at spirals at the seeds or the center of a sunflower, for example, you'll again observe patterns curving left and right. And if you count these spirals, your total is going to be a Fibonacci number. And if you divide the spirals into those pointing left and those pointing right, you're going to get 2 consecutive Fibonacci numbers. Just kind of blows the mind when you think of it that way. And yet there's even more, because there's a special relationship between Fibonacci numbers and something called the golden ratio. So the golden ratio describes when a line is divided into 2 parts, and a longer part here, A, is divided by the smaller part, B, and that division is also equal to the sum of A plus B divided by A. And by the way, that ratio, so you can see here the 2 sides, this is sometimes referred to as golden rectangle, and it expresses the golden ratio in exactly this fashion. Okay, so the A is the shorter of the 2 sides, and then the length is given by A plus B. And if you actually calculate the ratio, it always comes out to be the same, 1.618. Okay. So, and then lo and behold, as it happens, when we take any 2 successive Fibonacci numbers, one after the other, their ratio is very similar to, very close to the golden ratio. Again, let me restate that. The ratio of any 2 successive Fibonacci numbers approximates the golden ratio, that value, it's also called phi, of 1.618. Technically, if you were to extend it further, being an irrational number, it's 1.61803398887, etc., non-repeating. And the bigger the pair of the Fibonacci numbers that you're comparing, the closer and closer we start to approximate the golden ratio. Okay, so again, if you just take the ratio of the, early on in the sequence, you've got the Fibonacci numbers 2 and 3, right? And then 2 plus 3 equals 5, so the next 2 would be 3 and 5. And so on. So the first ratio there of 3 to 2 is simply 1.5. The ratio of 5 to 3 is 1.6 repeating. The ratio of 8 to 5 is 1.6. The ratio of 13 to 8 is 1.625. And then we jump ahead and look at this ratio. There's 2 Fibonacci numbers, the 144. And then again, if you add the two numbers, 89, which is preceding 144, 89 and 144 is equal to 233. Look at the ratio there of 233 to 144. Again, these are Fibonacci numbers right next to each other. And that ratio comes out to be, lo and behold, 1.618, 055, blah, 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 right? And then we go up one more, 233 and 377. 377 divided by 233 is equal to 1.618, and so on. And it only hones in closer and closer and more precisely to the golden ratio, right? And so from there, mathematicians can calculate all sorts of additional relationships, and most importantly, we can use that information to do one other thing, and that is calculate the golden spirals. And these are, of course, beautiful in nature, and they do show up in nature. There are logarithmic spirals whose growth factor equals the golden ratio. So I've shown it there without the numbers. That's what it looks like. And then I put in the Fibonacci numbers as well, right? And so the golden ratio, and hence the Fibonacci sequence, is routinely found in nature. And it's routinely found in architecture and found in different kinds of art and so on. So it's such a fascinating subject matter and such a fascinating sequence, the Fibonacci sequence, that there's actually an entire scientific journal devoted to the mathematical topics that are related to the Fibonacci numbers. And it's called, appropriately, the Fibonacci Quarterly, published 4 times each year. So, In closing, nature obviously has its own beauty, but so does mathematics. And not surprisingly, the two intertwine inexorably. Nature and mathematics. It's an almost magical and mystical combination that produces some of the most beautiful and recurring patterns in all of nature. I'm just glad I'm not a rabbit. Our house would we'd run out of room in no time. So, anyway, until next time, may you and yours continue to create peace in your, let me get the full screen here. Continue to create peace in your lives and nurture love in your hearts. And be sure to give someone, anyone, maybe even a rabbit, a hug today. And we'll see you next time.